Okay, so in this video I'm going to be recording the solutions to the 2018 VCAA Further Mathematics Exam 2. So Exam 2 in Further Mathematics is a short answer exam comprising 60 marks completed in 90 minutes. For the purposes of these videos, I'll be recording the core section, which is 36 marks, and one of the 4 modules, the Matrices Module, which will be 12 marks. So not completing the full 90-minute paper. Okay, so let's get started on the data analysis. So question 1, we have a table of data here with 4 variables: city, congestion level, size, and increase in travel time in minutes per day. Okay, so let's get on to the questions. The data in Table 1 on page 2 relates to the impact of traffic congestion in 2016 on travel times in 23 cities in the United Kingdom, UK. The 4 variables in the dataset are city, congestion level, size, and increase in travel time, and it tells you how those things have been measured. So how many of the variables in this data set are categorical variables? So I guess the question really is which ones are numerical and then the others are categorical. So increase in travel time is definitely a numerical variable, but the other 3 are all categorical. City is just the name of the city. Congestion level is grouped into 3 categories: high, medium and low. Size is grouped into 2 categories: large and small. So there are 3 categorical variables. 3, city, congestion level, and size. How many variables in this data set are ordinal variables? So ordinal is a type of categorical variable, so that would be categories where there is an implied order. City, there's definitely no implied order, but both congestion level and size have an order implied: high, medium, low, large and small. There's an implied order in those. So I would say 2 ordinal variables, which are congestion level and size. Name the large UK cities with a medium level of traffic congestion. Okay, so we're looking for cities which are size large and congestion medium. So let's go back to the data table. Fortunately, the table's organised by, oh no, it's not, sorry. It's organised by congestion level though. So we want medium congestion and large size. So medium congestion and large size, Newcastle, Sunderland, and Liverpool are going to be the 2 cities. So we want to name those 2 cities. Newcastle, Sunderland, and Liverpool. Okay, use the data in Table 1 to complete the following two-way frequency table in Table 2. Okay, so we want to group the data according to city size and congestion level. So let's just go one at a time. So we've already started looking at large cities with medium traffic, which would be this category over here. So we know that there were only 2 of those. So there were 2 large cities with medium traffic. Let's have a look at which way, doesn't really matter. Large cities with high congestion. So high congestion and large. High and large is going to be those 2. So 2 cities, London and Manchester. High and large. Let's have a look at small and medium. So small city size, medium congestion. Okay, so medium congestion is all grouped here, and those with small city sizes are 1, 2, 3, and 4. Okay. And then let's look to the small city size and low congestion. Small city size and low congestion. Okay, so small and low congestion is going to be 1, 2, 3, 4, 5, 6, 7, 8 cities with small size and low congestion. and then we want large size and low congestion, so that should be the remaining. So we've got 1, 2, 3 low congestion but large size. Okay, so then we should be able to add up. We should have a total of 7 large cities, and we've already calculated the total of 16, so we actually could have used that. We should be able to confirm that that adds to 16, which it does. Let's maybe just check that there are 7 large cities, and then that will confirm that we've found all the correct data values. So large cities, 1, 2, 3, 4, 5, 6, 7. Yes, good. Okay, happy that our data is correct. So what percentage of the small cities have a high level of traffic congestion? So of the small cities, so your denominator is the total number of small cities, which is 16. Out of the small cities, out of the 16 cities, how many have a high level of traffic congestion? So that is 4 out of 16. And changing that to a percentage, 4/16 is a quarter, so that's 25%. But again, you can get your CAS to do it for you. 4 over 16 times by 100, 25%. Okay, question part F. Traffic congestion can lead to an increase in travel times in cities. The dot plot and box plot below both show the increase in travel time due to traffic congestion in minutes per day for the 23 UK cities. Okay, so we've got the data presented both as a dot plot, which gives us the actual data values, and also as a box plot, which gives us obviously the 5-figure summary for the data. Describe the shape of the distribution of the increase in travel time for the 23 cities. Okay, so it's definitely got positive skew. Both the box and the median within the box are towards the left-hand side, so we have positive skew. It looks like from the dot plot it's possible that there is an outlier, but our box plot doesn't show any outliers, and so there are no outliers. You would need to mention outliers as part of the shape if there were outliers. So the shape of the distribution is positively skewed. Okay, part G, the data value 52 is below the upper fence and is not an outlier, which is what we were seeing the box plot show. Determine the value of the upper fence. Okay, so it's really important. I was going to say we can't read the upper fence off the box plot, but that would be a temptation from people if the box plot showed an outlier, but it's not a temptation here. So to determine the value of the upper fence, we're going to need both the quartiles, lower and upper quartiles, so we can calculate interquartile range. So let's see if we can read these off the plot. So if they're nice precise values, and it looks like they are, we can read them as 39 and 30. So the interquartile range is Q3 minus Q1. So that is 39 minus 30, which is 9. And then the upper fence is Q3 plus 1.5 times the interquartile range. Q3 is 39 plus 1.5 times our interquartile range, which is 9. Okay, so 39 plus 1.5 times 9 is 52.5. So we don't need to make any statement about that. The question already makes the statement that the data value 52 is below the upper fence and is not an outlier, but our upper fence certainly is confirming that. We definitely expected to get a value bigger than 52. But it makes sense that it's pretty close to 52. Looking at the dot plot, you can see that 52 is almost an outlier, it's just not quite. The upper fence is here, and so therefore it is included in the box plot. Okay, so question 2. The congestion level in a city can also be recorded as the percentage increase in travel time due to traffic congestion in peak periods compared to non-peak periods. This is called the percentage congestion level. The percentage congestion levels for the morning and evening peak periods for 19 large cities are plotted on the scatter plot below. Determine the median percentage congestion level for the morning peak period and the evening peak period. Write your answers in the appropriate boxes below. Okay, so we've got morning congestion level on the horizontal axis, so the explanatory variable, and evening congestion level on the vertical axis, so the response variable. Now we know that we've got 19 large cities, okay? So that means that the median is the 19 plus 1 divided by 2, so the 10th value. Okay, so when we're looking, let's focus first of all on the morning congestion level. So this is the smallest value here. This is the second smallest, so we're looking for the 10th smallest. 3, 4, 5, 6, 7, 8, 9, 10. Right. So that is going to be the median morning congestion level. So reading our scale correctly, it should be at 52%, the median percentage congestion for morning peak, so 52. And then it's also going to be the 10th value, but the 10th value looking at the evening congestion. So the lowest evening congestion is 41. Oops. The second one is here, 2, 3, 4. There's actually 2 data values with that value. There's another 2 here. 5, 6, 7, 8, 9. So it'll be this one will be the 10th data value. So that means there's another 9 data values higher than this and 9 values below. So that should be 56%. Okay, let's clear off our plot in case we need it for something else. A least squares line is to be fitted to the data with the aim of predicting evening congestion level from morning congestion level. The equation of this line is evening congestion level equals 8.48 plus 0.922 times the morning congestion level. Name the response variable in this equation. Okay, so we can see from the equation that this is going to be the response. We can also see from the scatter plot that this is going to be the response. We can also read it from the sentence. A least squares line is to be fitted with the aim of predicting evening congestion is the response. Okay, so 3 ways to tell that. More than enough information to work out what the response variable is. Sorry, evening, I can't write and say a different word at the same time. Evening congestion level is the response variable. Okay, part C. Use the equation of the least squares line to predict the evening congestion level when the morning congestion level is 60%. Okay, so we've got our equation. Now, it's important to understand that the variables are in percentages, so when we substitute 60% in place of the morning congestion and looking at the scale here, we won't write 0.6, we'll write 60. Okay, so it's going to be evening congestion level. Can't keep them both on the same. Let me just change the scroll for a minute so I can keep them both here. Alright, so evening congestion, so predicted evening congestion is going to be 8.48 plus 0.922 times the morning congestion, which is 60. So 8.48 plus 0.922 times 60, and we want, it doesn't tell us to round, so we won't round that off. It says it is, it is 63.8%, the predicted evening congestion. Okay, part D. Determine the residual value when the equation of the least squares line is used to predict the evening congestion level when the morning congestion level is 47%. Okay, so we need to do what we just did for the 60%, but we need to do it with 47 this time. So the predicted evening congestion is 8.48 plus 0.922 times 47 this time. So that's going to be easy in my CAS because I've done that calculation once, so I'm just scrolling up, copying down, to, pressing enter to copy that down and changing the 60 to 47. So that is 51.814, okay? And so the residual is going to be the actual minus the predicted. So we've worked out the predicted is 51.814. Now we want the actual evening congestion when the morning is 47%. So we're going to need to go up to our plot. So when the morning congestion is 47%, which is here, the actual evening congestion is 50%. Okay. So it's going to be 50 minus 51.84, and we want the residual correct to 1 decimal place, so 50 minus this value is negative 1.814, so to 1 decimal place is negative 1.8. Okay, the value of the correlation coefficient R is 0.92. What percentage of the variation in the evening congestion level can be explained by the variation in the morning congestion level? So this is simply R squared, which is 0.92 squared, so 0.92 squared, which is 0.8464, and we want what percentage to the nearest whole number. So as a percent, we multiply by 100, so that's going to be 84.64%. To the nearest whole number is 85%. Okay, you don't need to rewrite out this sentence. I'm finding a lot of my students are doing that unnecessarily. If the question asked us to interpret the value of the correlation of the coefficient of determination, we would need to say the coefficient of determination tells us that 85% of the variation in evening congestion level can be explained by the variation in morning congestion level, but that's not what the question asks us. It says what percentage of da 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 da. Okay, so it's already given us that sentence. We don't need to repeat it. 85% is all you need there for the mark. Okay, question 3. Table 3 shows the yearly average traffic congestion levels in 2 cities, Melbourne and Sydney, during the period 2008 to 2016. Also shown is a time series plot of the same data. The time series plot for Melbourne is incomplete. Okay, so we've got both the data and the almost complete time series plot. Use the data in Table 3 to complete the time series plot above for Melbourne. Okay, so we're missing the 2014, 15 and 16 points for Melbourne, so that's going to be these values here. So 2014, the Melbourne's congestion level is 28%. We've got a nice precise scale here, so 28% is still here, which matches with, if you have a look, it should be the same as the last 3 years. Then in 2015 it goes up to 29%, and then in 2016 it jumps up to 33%, which should be up here. Okay, so we want to continue, we may need to make sure we join, but we also want to continue with the same type of line. Sorry, my computer pen jumped a little there. Let's try and get that a bit straighter. Okay, ideally use a ruler, but completing the plot, making sure that you're actually joining together those points as well. Okay, so a least squares line is used to model the trend in the time series plot for Sydney. The equation is, okay, so we've got that there, and we want to draw this least squares line on the time series plot on page 8. Okay, so let's go back up and look at the scale we've got here. So we're going to need to work out in 2008 what the congestion level is. So we want to put our year. I'm just checking that there isn't a year code. So no, year is literally 2008. Okay, so let's just work out when the year is 2008, which is the start of the plot. What is the congestion level? Okay, so negative 2280 plus 1.15 times 2008, 29.2. Okay, so 29.2. So it's going to start, I'm going to use a different colour actually. It's going to start somewhere about there. Okay, so it should be 2008, 29.2. And then let's work out what's happening in 2016, and we can join those 2 points with a straight line. So this time, when the year is 2016, I'll just edit my calculation in my CAS. It's 38.4, so 2016, 38.4. So 38.4 should be about here. So that is 2016, 38.4. Okay, and then I'm going to get a ruler, and I'm going to, well, my fictional ruler, and I'm going to join these up with a straight line. Do that again, I didn't really join properly here. There we go, that's better. Okay, so there's my least squares regression line. Oh, sorry, I've just realised I've actually plotted that 38.4 above 39 instead of above 38. Okay, so sorry, I'm just going to fix that. 38 is here, so 38.4 should actually be under there. Apologies for that. Okay, let's join those up with a straight line. It's really important that you use the scale accurately and that you use a ruler so it's a nice precise line. Alright, so now we've got our least squares regression line correct. Okay, so that was part 1 of part B. Use the equation of the least squares line to determine the average rate of increase in percentage congestion level for the period 2008 to 2016 in Sydney. Write your answer in the box below. Okay, so this is actually really just asking you for the slope of the line. So it's about understanding what that sentence is saying. So as the year increases by 1, the congestion increases by 1.15% on average, which is what the question's asking us about. So this should be 1.15%, which is just that value there. All that's asking you about is the slope. Use the least squares line to predict when the percentage congestion level in Sydney will be 43%. Okay, so this time we want to make congestion level 43%, okay, and solve to find what the year is. So the equation is going to be 43 equals negative 2280 plus 1.15 times the year. And so we can use our CAS to solve an equation for us. It's probably the most efficient way. 43 equals negative 2280 plus 1.15 times an unknown value, and we want to solve for that unknown value, and so we find that the year is equal to 2020. So least squares line predicts that percentage congestion level in Sydney will be 43% in the year 2020. Yearly average traffic congestion level data for Melbourne is repeated in table 4 below. Okay, good, so we don't have to keep scrolling up and down. When a least squares line is used to model the trend in the data for Melbourne, the intercept of this line is approximately negative $1,514.75556. Round this value to 4 significant figures. Okay, the first significant figure is the first non-zero digit in the number, wherever it appears. So that's the 1. So the 1 is the first significant figure. 5 is the second significant figure, 1 is the third significant figure, and 4 is the fourth significant figure. So we're going to be stopping there. We look to the 5th significant figure to see whether we should round up. It's bigger than 5, it's 5 or more, so we do round up. So this becomes negative 1515, correct to 4 significant figures. Use the data in table 4 to determine the equation of the least squares line that can be used to model the trend in the data for Melbourne. The variable year is the explanatory variable. Write the values of the intercept and the slope of this least squares line in the appropriate boxes. Okay, you've been given a gift here because they've just given you the intercept and you want to write it to 4 significant figures here in the line. So this should be negative 1515 here. So hopefully that's also going to be a nice check to make sure that we've entered our data in correctly. So I'm going to insert a lists and spreadsheets page to do the regression. I'm going to enter in the data. We're going to have variable year, and the other variable is going to be, I'm just going to write Melbourne for Melbourne. And I'm just going to write Mel for Melbourne, I mean. Okay, I'll just pause the video while I enter in the data. Okay, so I've got the data entered in. And now I'm going to do the regression. So menu 414. My X list is year. My explanatory variable. And my Y list, my response variable is Mel. Okay, and it should confirm for me, good, that I've got the same y-intercept that they gave in the question up here. If you have a look at the number down the bottom line of the CAS screen, you can see that number in full, and it certainly does seem to match what we have written up there, so that's all good. To 4 significant figures, we already know that's negative 1515. And then B, we also want to give that to 4 significant figures, so that is going to be 0. Now 7 is the first significant figure, second significant figure, third significant figure. Now the fourth significant figure is a 6, but the number after that's also a 6, so we should round it up to 7. So both values to 4 significant figures, negative 1515.7667. Okay, question part E. Since 2008, the equations of the least squares lines for Sydney and Melbourne have predicted that future traffic congestion levels in Sydney will always exceed future traffic congestion levels in Melbourne. Explain why, quoting the values of appropriate statistics. Okay, so we've got our Melbourne congestion level least squares regression line, which predicts the congestion levels. and it's negative 1515. Now I'm just going to have a look at the plot here, up here. So I'm going to plot it on here. So I'm going to also work out 2008 and 2016, the congestion levels in those 2 years for the Melbourne congestion. Okay, so we're going to have, sorry, just going to go back out to here. All right, negative 1515 plus 0.7667 times 2008 is 24.5, and then 2016, 30.7. Okay, so 24.5. So the Melbourne line would be from 24.5 to 30.6. 30.6, which is going to be about there. Okay, so it certainly does seem that the Melbourne line, oh sorry, I just put that in the wrong place. I would to draw it in. The Melbourne line is definitely below the Sydney line, but we want to use statistics to confirm that for us. So we want to know that from 2008, the Sydney congestion will always be higher than the Melbourne congestion. And there are two key things that are important. The first thing is that the starting value in 2008 is the Sydney value is higher than the Melbourne value. Okay, so that tells us that Sydney started off with higher congestion in 2008. And then the second thing is, we can see this from the lines, that the Sydney line has a steeper slope than the Melbourne's line. So because the Sydney line is increasing at a faster rate and the Melbourne line is not increasing so quickly, they're not going to cross. Okay, if the Melbourne line had a steeper gradient than the Sydney line, then they would have to cross at some point, even if it was later on. Okay, now we can confirm using actual values from the least squares regression equation that the 2008 value is predicted value from the regression line is lower. We've got it up here. It's higher, 29.2 compared to 24.5. Okay, in 2008, and we can also confirm from the regression equations that the slope, the Sydney slope, is 1.15. So we're increasing on average by 1.15% every year, whereas the Melbourne congestion is only increasing on average by 0.77% per year. So 0.77% per year. Okay, so we want to quote those things here. So in 2008, congestion in Sydney, congestion levels in Sydney, which were 29.2%, were higher than those in Melbourne. Which is the Melbourne one in 2008, I've got the numbers over here in my CAS, was 24.5%. From 2008, congestion levels in Sydney are increasing at a rate of 1.15% per year, compared to Melbourne, which is increasing at a rate of 0.77% per year. Since Sydney's congestion starts out higher in 2008 and increases at a fast, and is predicted to increase, and is predicted to increase at a higher rate than Melbourne's, at a higher rate. it is always predicted to have higher congestion than Melbourne. Okay, so the key things here, and in having a look at the examiner's report here, the key things here are to be comparing both the 2008 values and the relative slopes. So you want to make mention of both of those statistics, that Sydney starts out higher in 2008 and that its rate of increase, its slope, is higher than Melbourne's. So those two, those are the statistics that need to be quoted, and you must make sure that you are always making comparative statements, that Sydney's is greater than Melbourne. You can't just state the values and expect the reader to interpret which one's greater. You have to make the clarification that Sydney starts with higher congestion levels in 2008 and its congestion levels are increasing at a greater level than Melbourne's, and use the data to support that. One of the other comments in the examiner's report is that some students used the starting values from the actual data values, whereas the question asks you since 2008, the equations of the least squares lines have predicted that. So you're comparing the values from the least squares regression lines. You're comparing what the predictions are based on those equations. Okay, moving on to the recursion and financial modelling. So question 4. Julie deposits some money into a savings account that will pay compound interest every month. The balance of Julie's account in dollars after n months, Vn, can be modelled by the recurrence relation shown below. How many dollars does Julie initially invest? Okay, so that's V0. So she initially invests $12,000. Recursion can be used to calculate the balance of the account after 1 month. Write down a calculation to show that the balance in the account after 1 month, V1, is $12,074.40. So you actually have to write down the calculation. So we know that V1 is 1.0062 times V0, which is 12,000. And so therefore, let's just check that it actually gives the value so that we know that we've written down the right calculation. It is indeed $12,074.40. Just checking the rounding there. Yep. Okay. So it's 1 mark. It's not for the value. You were given the value in the question. The 1 mark is for writing down a calculation. After how many months will the balance of Julie's account first exceed $12,300? Okay, I would just use recursion with my CAS. So it starts at 12,000, okay, and then we multiply by 1.0062. So after 1 month, 2 months, 3 months, what do we want? 12,300. Up to 3 months, 4 months. So it's just over 12,300 at the 4 month mark. So V4 is 12,338 cents. So therefore, it'll be after 4 months. Okay, a rule of the form Vn equals a times b to the power of n can be used to determine the balance of Julie's account after n months. Okay, so because she's not also got payments going in or out, it's simply the interest being added each month. We can convert this recurrence relation, so just geometric growth, we can convert the recurrence relation into a rule. And so the balance at any time, n, will be her initial $12,000 multiplied by the percentage change, which is the multiplying by 1.0062 every month, 1.0062, and we do that n times depending on how many months. What would be the value of n if Julie wanted to determine the value of her investment after 3 years? Okay, so 3 years is 36 months, which means that n would be 36. Okay, question 5. After 3 years, Julie withdraws $14,000 from her account to purchase a car for her business. For tax purposes, she plans to depreciate the value of her car using the reducing balance method. The value of Julie's car in dollars after n years, Cn, can be modelled by the recurrence relation shown below. So C0 is $14,000, the initial value of her car is $14,000. And then we are going to be multiplying by something each year. For each of the first 3 years of reducing balance depreciation, the value of R is 0.85. What is the annual rate of depreciation in the value of the car during these 3 years? So what this means is every year we are finding 85% of the previous year's value. So we don't still have 100% of the value, it's reduced to only 85% of the value, which means the rate of depreciation has been 15%, 100% minus 85%. For the next 5 years of reducing balance depreciation, the annual rate of depreciation in the value of the car is changed to 8.6%. What is the value of the car 8 years after it was purchased? Okay, so depreciation of 8.6% per annum means that we're multiplying by, every year we're being left with 100 minus 8.6, we're being left with 91.4%, and so we are multiplying by 0.914 every year. Okay, so our recurrence relation is C0 is 14,000. No, we first need to work out, sorry, so we need to do the first 3 years of, sorry, what did we do? So the first 3 years was at this rate, okay? So let me just move that calculation down, sorry, because we'll need that in a bit, but not yet. I'll move it back to wherever I need it in a minute. Okay, so the first 3 years, okay, we know that C0 is $14,000 and Cn plus 1 is 0.85 times Cn. Okay, so that means we want to know what C3 is, so 14,000. Multiply that by 0.85, so after 1 year it's that, 2 years, 3 years. So C3 is $8,597.75. Okay, so then that becomes, then it's going to be the next 5 years. Okay, this time C0 is now that, 8597.75. And Cn plus 1, well, we can still call it C3, but that's where we're starting, okay? And Cn plus 1 is now going to be, what did we just say? Is going to be this rate of depreciation, 0.914 times Cn. So therefore, we're now going to start taking this value here, that value, and we're going to multiply that by 0.914 for another, what do we want to know? Next 5 years, for another 5 years. So that's C3. So we want to get to C8, really. So that's C4, 5, 6, 7, 8. So I've done that recurrence. Okay, so that means that C8 is going to be $5,484.23. The value of the car 8 years after it was purchased is going to be $5,484.23. Okay, so question 6. Julie has retired from work and has received a superannuation payment of $492,800. She has 2 options for investing her money. Julie could invest the $492,800 in a perpetuity. She would then receive $887.04 each fortnight for the rest of her life. At what annual percentage rate is interest earned by this perpetuity? Okay, so the payment is equivalent to the interest. Okay, so this is the monthly interest. Fortnightly interest. So that's the fortnightly interest because it's a perpetuity. And so therefore we want to work out what that is as a percentage of the initial investment. So 88. So the fortnightly rate is 887.04 divided by 492,800 times by 100% to convert it to a percentage. So let's do that. 887.04 divided by 492,800 times by 100. Okay, so that is not approximately equal to, it actually equals 0.18%. And so then the annual rate is going to be 0.18% multiplied by, so there's 26 fortnights in a year, and so that is 4.68% per annum. Okay, option 2 for her investment is that she could invest the $492,800 in an annuity instead of a perpetuity. The annuity earns interest at the rate of 4.32% per annum, compounding monthly. The balance of Julie's annuity at the end of the first year of the investment would be $480,242.25. What monthly payment would Julie receive? Okay, so we're going to need our finance solver. Okay, now N is going to be, so she's getting monthly payments and we want to know end of 1 year, so N is going to be 12. The interest rate we know is 4.32. The principal value, the present value, is going to be the initial amount she invests, and she's investing it, so it's negative, going away from her to the bank, negative 492,800. The payment is what we're trying to work out, and we know the future value is going to be this. Now that's her money, so that's positive money in relation to her, $480,242.25, and the payments per year and compounds per year are monthly, so 12. Alright, so we work all that out, and let's put that in, so 12, 4.32, negative 492,800, payments what we're trying to work out, future value is 480,242.25, and monthly, so 12 payments per year, compounds per year. Alright, enter on the payment, and so the payment is going to be, and it's positive because it's coming from her investment to her, so from the bank to her, so it's $2,800 in dollars. In dollars is a slightly vague instruction actually, because it doesn't mean to the nearest dollar. So the default instruction is to the nearest cent. So I would be inclined to give the 0.00 because it doesn't actually tell you to round differently, and the standard instruction in the Recursion and Financial Modelling section is always to give your answers to the nearest cent. It says that in the instructions at the beginning. It's something you should be familiar with every time you do a further maths paper. We're right back to the start here. And key instruction. In Recursion and Financial Modelling, all answers should be rounded to the nearest cent unless otherwise instructed. So strictly speaking, in this question we just did, we weren't otherwise instructed to round. It doesn't say round to the nearest dollar, it says give your answer in dollars. Like $2,800.32 is still in dollars. So just be a bit careful about that. To be honest, I doubt they would have penalised if you just wrote 2,800, but strictly speaking, according to the wording there, it should be rounded to the nearest cent. Part 2. How much interest would Julie's annuity earn in the second year of investment? Okay, so we know at the end of, so the second year is from the end of the first year to the end of the second year. That is the second year. Okay, the first year is from the beginning to the end of the first year. So therefore we know that the value at the end of the first year is $480,242.25, and then we can work out using our finance solver the end of the second year. Okay, so now we're going to make our payment exactly that. Our principal value here is, actually we don't need to change that, hold on, let me undo. I can't. I'm just going to put that back to what it was, 492,800, because nothing changes in the second year, so I can just work out. Okay, I'm going to round the payment off though. I can now just change the N value to 24 to work out what the value is after 2 years, and work out the new future value. Okay, so it should be end of the second year would be 467,000. Oh, $67,131.14 to the nearest cent. Yeah, you could have by all means changed the principal value, left in at 12 months, and then worked out the new future value. Either way, should give you the same thing. So how much interest would Julie's annuity earn in the second year of investment? Okay, so we've worked out the value of the investment at the end of the first year and the end of the second year. Okay, so we want the change in the balance during the second year, during year 2, is going to be 480,242.25, take away 467,131.14. Okay, so oops, let's escape out of there. Let's work that out. 480,242.25 take away 467,131.14. Okay, so the change in the balance is 13111.11. Okay, so it's gone down by that amount, but at the same time she's also taken out 12 payments. Okay, so the payments that she's taken out in that time is 12 payments of $2,800. So 12 times 2,800, oops. She's taken out payments of 3,600. Okay, so the balance has actually only reduced by $13,000, even though she's actually taken out more than $33,000. So that means that the interest that she's earned in that time is the difference between those two values. So 33,600 minus 13,111.11 cents. And so the interest is going to be that minus that. So during the second year, she's earned $20,488.89 in interest. It was also noted in the examiner's report that students who had used an unrounded payment value and or possibly an unrounded end of second year value along the way got a 88.88 here, and that was also accepted. So I want to be clear about the fact that if you work more precisely in your calculations by not using rounded values along the way, you should never be penalised in the VCAA exam, and usually they work out the numbers so that you actually get the same answer either way. So actually what they normally would have done is asked for this to the nearest dollar, and then that would have avoided the different rounding errors, the different roundings depending on how accurately you worked. But in this case they did explicitly state that they also accepted 0.88 because it was a result of actually more accurate working. Okay, now we're into the modules. So we'll have a look at the Matrices module. So let's get started here. Question 1. A toll road is divided into 3 sections, E, F and G. The cost in dollars to drive one journey on each section is shown in matrix C below. What is the cost of one journey on section G? Okay, so that's just simply drawing the correct number out of this matrix, $2.87 for one journey on section G of the toll road. Write down the order of matrix C. It's got 3 rows and 1 column, so it's a 3 by 1 matrix. Part C. One day Kim travels once on section E and twice on section G. His total toll cost for this day can be found by the matrix product M times C. Write down the matrix M. Okay, so we're going to need M times C has to be some matrix multiplied by C, which is 3.58, 2.22, and 2.87. And we want that to give his total cost. So we want that to give a 1 by 1. And this is a 3 by 1. And so we're going to need a 1 by 3. Okay. Now we want Kim to travel once on section E. So which one was which? So these were E, F, and G. So we want the calculation to do one lot of 3.58, which would mean putting a 1 here. And twice on section G. So no times on section F, so we want 0 times $2.22, and we want 2 times $2.87. And that should then do 1 times $3.58 plus 0 times $2.22 plus 2 times $2.87. So it should give us 1 times 3.58 plus 2 times 2.87 is 9.32. So $9.32. So M, the matrix M that we would need to calculate that would be 1, 0, 2, a 1 by 3 matrix. Okay, question 2. The West Horn Council must prepare West Horn or West Thorn, who knows? Council must prepare roads for expected population changes in each of 3 locations: main town M, villages V, and rural areas R. The population of each of these locations in 2018 is shown in matrix P 2018 below. The expected annual change in population in each location is shown in the table below. Okay, so main town is going to increase by 4% each year, villages are going to decrease by 1% each year, and rural areas are going to decrease by 2% each year. Write down matrix P 2019, which shows the expected population in each location in 2019. Okay, so 2019, we simply need to increase the main town value by 4%. So that is to multiply it by 1.04. Okay, so it's going to be 2100 times 1.04 is a 4% increase, so that becomes 2184. The village population decreases by 1%, so that isn't to take away anything, that is to end up with only 99%. So multiply by 0.99, so 1800 times 0.99 is going to be 11782. And the rural area population decreases by 2%. So again, we're not taking away anything, we're ending up with 98% of what we started with, so multiplying by 0.98. So 1700 times 0.98. So that is 1666. The expected population in each of the 3 locations in 2019 can be determined from the matrix product P 2019 equals F times P 2018. Okay, so we want to think about P 2019 was a 3 by 1 matrix. That's going to be multiplied by, it's going to be F times P 2018, which was also a 3 by 1 matrix. Okay, so we need this F matrix is going to have to be a 3 by 3 matrix, so that when we multiply it by a 3 by 1 matrix, it's possible, and so that it gives us a 3 by 1 matrix. So F needs to be a 3 by 3 matrix, okay, and it needs to be such that it does, so what were our original numbers here? 2100, 1800, and 1700. It needs to multiply that number by 1.04 to give us this. It needs to multiply that number by 0.99, and it needs to multiply that number by 0.98. So we're going to do, I'm going to put 1.04 up here. That would do, so thinking about this number in the top of our answer is going to be the top row times the only column, and I need it to be 1.04 times 2100. So I need a 1.04 here, plus we want 0 times 1800, so we're going to need 0, plus 0 times 1700, so we're going to need 0 there. Okay, so then for the number in the second row, we know that's got to be 1800 times 0.99. So we want this row here times the column to simply do 0.99 times 1800. So we want 0 lots of 2100, 0.99 times 1800, and 0 lots of 1700. Okay, and then hopefully you can see the pattern here now, that for this bottom number here, we're going to want the bottom row times the column to simply do 0.98 times 1700. So we're going to need 0 lots of 2100, 0 lots of 1800, and 0.98 lots of 1700. Okay, so F is a 3 by 3 matrix with 1.04, 0, 0, 0.9, sorry, that was 0.99, that middle one, wasn't it? 0.990, and 0, 0.98. And there is F. Okay, question 3. The High Roads Company has a contract to maintain and improve 2,700 kilometres of highway. Each year, sections of highway must be graded, resurfaced, or sealed. The remaining highway will need no maintenance, which is denoted by N. Let Sn be the state matrix that shows the highway maintenance schedule for the nth year after 2018. The maintenance schedule for 2018 is shown in matrix S0 below. So of the total 2,700 kilometres of highway, 700 is due to be graded in 2018, 400 is due to be resurfaced, 200 kilometres due to be sealed, and 1,400 kilometres need no maintenance in 2018. The type of maintenance in sections of highway varies from year to year, as shown in the transition matrix below. Okay, so we see that 20% of the highway that was graded last year will be graded again the next year. 10% of the highway that was graded last year will be resurfaced next year. 50% of highway that had no maintenance this year will still need no maintenance next year, etc. All right. Of the length of highway that was graded in 2018, how many, so that was 700 kilometres, so out of 700 kilometres, that's going to be the denominator, how many kilometres are expected to be resurfaced the following year? Okay, so it's not a percentage, sorry, but it's just out of these 700, how many kilometres are expected to be resurfaced the following year? Okay, so we want to know how many go from being graded one year to resurfaced the next year. So that's 10%, and there was 700 kilometres initially. So it's 700 times 0.1, 10% of 700 kilometres. So that is 70. You can check it with your CAS. Oh, sorry, 700 times 0.1 should be 70 kilometres. So of the 700 kilometres that were being graded in 2018, 70 kilometres out of that will next year be being resurfaced. Show that the length of highway that is to be graded in 2019 is 460 kilometres by writing the appropriate numbers in the boxes below. Okay, so if we were going to be working out the 2019 numbers, we would be doing our transition matrix multiplied by the 2018 numbers, which are 700, 400, 200, 1400. And to work out, that would give us the 2019 numbers, okay, and we're interested in the numbers that are to be graded, so that's the top row here. So we want to know how this top number arrives, and we arrive at this top number by doing the top row of the transition matrix times the column of the 2018 matrix, which means the calculation is going to be 0.2 times 700 plus 0.1 times 400 plus 0.0 times 200 plus 0.2 times 100. And we should be able to check our answer by checking that when we actually do that, we get 460. 0.2 times 700 plus 0.1 times 400 plus 0 times 200, which we don't really need to worry about, plus 0.2 times 1400. So that is indeed 460. Okay. The state matrix describing the highway maintenance schedule for the nth year after 2018 is given by this. Okay, so there's no other changes other than caused by the transition matrix. Complete the state matrix S1 below for highway maintenance schedule for 2019. Okay, so we've already worked out this value in the previous calculation. They're giving us this one here, but really we need to do the matrix multiplication to work out S1 anyway. Okay, so we know S1 is T times S0. So we're going to get our transition matrix, which we've got here, times S0, which we've got up here. So let's do that in our CAS. So we need a 4x4 matrix, the transition matrix, 0.2, oops, sorry. So 0.2, 0.1, tab, not scratchpad, 0.2. The second row is 0.1, 0.1, 0, 0.2. The third row is 0.2, 0.1, 0.2 and 0.1, and the fourth row is 0.5. Oh, sorry, struggling today. 0.1, 0.7, sorry, 0.5, 0.7, 0.8, 0.5. Okay, so transition matrix multiplied by S0, which is 2018, so that is a 4x1 matrix. So 700, 400, 200, 1400. Okay, so that's S1, which is the 2019 numbers. So 460 is confirmed, 390, 360 and 1490 is also confirmed. So nice little checks to make sure that we've got our answer right. There should be no reason for getting that wrong. In 2020, 1,536 kilometres of highway is expected to require no maintenance. Of these kilometres, what percentage is expected to have no maintenance in 2019? Okay, so therefore we know in 2020 there'll be 1,536 kilometres requiring no maintenance. Of these kilometres, what percentage is expected to have had no maintenance in 2019? So we want to know, we know that this many had no maintenance in 2019, and we know from the transition matrix that 50% go from having no maintenance one year to still needing no maintenance the next year. Okay, so it's going to be 50% of the 1490 is the number of kilometres that had no maintenance last year that will need no maintenance this year. Sorry, no maintenance in 2019 that will need no maintenance in 2020. So it's 0.5 times 1490, which is 745 kilometres. Okay, so of the 1536 kilometres that will need no maintenance in 2020, this many kilometres had no maintenance in 2019. So we want that as a percentage. So 745 out of 1,536, multiplying by 100% to change that to a percentage. 745 divided by 1536 times by 100. So we want our answer to one decimal place. That is 48.5% to one decimal place. Okay, E, in the long term, what percentage of highway each year is expected to have no maintenance? So we want to work out the steady state matrix, which means applying a high number of transitions to our initial state. I usually use 50. So 50 transitions to the initial state should get me to the steady state. To check that I've reached the steady state, I should also check that 51 transitions keeps me in the same place. So 431.56, yeah, certainly to two decimal places at least the values are the same, and that's more than enough. In the long term, what percentage of highway each year is expected to have no maintenance? So the steady state matrix is 432 kilometres, 388 kilometres, and, oh sorry, there's 4 rows in it. So 432, I'm just rounding to the nearest kilometre. We just want to be a bit careful about the rounding here though. 388, 348, and 1532. So let's just check the sum of that. So 432 plus, it should still be the original, I think it was 2,700, wasn't it? The highway hasn't grown, so it should still be the same number of kilometres in the long run. Plus 388, plus 348, plus 1532. Good. Okay. So in the long term, what percentage of highway is expected to have no maintenance? So in the long term, it's this many kilometres. So the long term percentage is 1532 kilometres out of the total 2,700 kilometres times 100% to convert it to a percentage. We want our answer to one decimal place. 1532 divided by 2,700 times 100 is going to be 56.7% correct to one decimal place. Okay. Question 4. Beginning in the year 2021, a new company will take over maintenance of the same 2,700 kilometres of highway with a new contract. Let MN be the state matrix that shows the highway maintenance schedule of this company for the nth year after 2020. The maintenance schedule for 2020 is shown in the matrix M0 below. For these 2,700 kilometres of highway, the matrix recurrence relation shown below can be used to determine the number of kilometres of this highway that will require each type of maintenance from year to year. Okay, so now we've got a transition matrix. Oh, sorry. Now we've got a transition matrix that's going to be, changing the various kilometres, but also we've got a, we're also adding and subtracting each year, just a fixed number of kilometres. Okay, write down the value of k in matrix B. All right, so the key thing here is that there's no suggestion, it's the same 2,700 kilometres of highway. There's no suggestion that there's, and it's still talking about the 2,700 kilometres of highway for the recurrence relation. So we're not growing the highway. So therefore, the total changes that we're making have to total out to be 0. If we're adding 20 kilometres into the resurfacing section each year, and we're adding 10 kilometres into the sealing section each year, and we're taking 60 kilometres out of the total amount that needs no maintenance, then K must, whatever that value has to be, the amount that's being graded has to make sure that there is, 0 change in total. So we essentially need, this to add up to 0. So at the moment we've got 30 kilometres being added in and 60 kilometres being taken out. So there's going to need to be another 30 kilometres taken out here. So K has to be negative 30 in order to make sure that overall the road isn't changing its length. Okay. How many kilometres of highway are expected to be graded in the year 2020? Okay, so we've got, 2022. So we've got 2020, so we need to make 2 transitions. And when you've got a plus b on the end here, you can't simply do t squared. You have to do the 2 transitions. Okay, so we need to first of all work out 2021 is going to be m1. All right, and that is going to be t times m0 plus b. And so we'll work that out. I'm hoping the transition matrix is still the same transition matrix. Let me go back here and grab that and just check. 0.2. Yes, okay. So I'm going to delete that para 51, which we don't want. I'm going to change the numbers here to make it m0, so that should be 500, that's still 400. This should be 300, and this should be 1500. Okay, so that is transition matrix times m0, and then we're going to have plus b. So plus another 4x1 matrix, which is negative 30, positive 20, positive 10, and negative 60. Oh, it's not negative 30, sorry. That doesn't add up to 0 at all. My apologies, it should still be positive 30, okay? Sorry, that was my error. So that should be positive 30, which means we're adding in 60 there, and we're taking away 60 there. So it's all good. Sorry about that. So it shouldn't be negative 30 up here. It should be positive 30. I was going to say I was going to use this question to check that we did still have 2,700 kilometres of road, which we would have realised we didn't when we did it. So, you want to take these opportunities to check, because this is your chance to check that you've got B right. So we should find 470 plus 410 plus 360 plus 1460 is still 2,700. So that confirms that our K value is correct now that we've fixed it. Okay, so 470, 410, 360 and 1460. Okay, so that is 2021's numbers. We want 2022, so we now need to calculate M2, which is the transition matrix times M1 plus B. Okay, so we want to do this same calculation that we did up here, except we want this matrix to be replaced by this one, which was M1. Okay, and we've got 457, 400, 363, and 1480. And we want the proportion that should be graded. Graded is the top row, not the proportion, sorry, the number of kilometres that should be graded. So therefore 457 kilometres to be graded in 2022. It's really important that if you're being asked for a specific value, that you actually extract that value out of the matrix and answer the question. If you're asked for how many kilometres are expected to do one particular thing, don't give a matrix as your answer. You need to actually articulate which number from that matrix is relevant. Okay, so I think that's the end of the Matrices module. Just checking here. Yes. Okay, so that's as far as I'm going to go in the 2018 Further Maths Exam 2. I hope some of that might have been helpful.